And now everybody can see my right?
Not yet. We don't see the screen. You might have shared the wrong screen if you have two screens.
Now,
Yep, just put it in full screen. Oh, yep, perfect.
so good afternoon, everybody. As Dr. Karamudi mentioned, my name is Tadewos. The title of today's presentation, my talk will be on decentralized testing of autonomous vehicles. So the motivation behind our research is to enable autonomous agents or to provide autonomous agents the capability to mimic human-like behavior. On the left, you can see certain search and rescue mission. Here, we need a highly specialized personnel or operators for the search and rescue operation. For the robot to mimic this kind of advanced features, the robot must be able to perform instantaneous decision, and also it must collaborate among its peers or among agents just to perform an action or a task. So that will be the focus of my talk today. So my presentation, I will start with motivation. I will go to background. I will provide the proposed behavior solution. I will introduce the problem formulation. I will discuss the details of our algorithm, and I will show implementation and go through the case. So as background, systems, basically multi-agent systems are multiple agents that can interact with each other to accomplish a task. So here we can see a team of agents performing warehouse management activity. We can see fleet of
the screen. Okay, let me come over because I'm recording it. I don't see what's going on. Right.
I'm sorry. Okay. Here we see fleet of tractors performing agricultural activity. We can see convoy of a convoy of vehicles performing transportation. Here we can see a team of robots performing search and rescue operations. So why multi-agent system? Basically, we can say the main reason can be, we can consider that some tasks they require, or it is a must to have multiple agents, like exploration, game of football, and other applications they require cooperation. In addition to that, we can increase efficiency. Multi-agent systems allow parallel operations, they increase robustness, they increase fault tolerance capability, and they increase flexibility of execution. And now we have a big infrastructure. So to take advantage of big infrastructure, having multi-agent system allow us to facilitate execution by taking advantage of distributed sensing or available infrastructures. So even if multi-agent systems have many attributes, we will be focusing on autonomy, distributed decision, and collaboration. Autonomy is the ability of the agent to synthesize a course of action or a plan to perform a task or a task. Distributed decision making is once a task or an action is assigned to an agent is responsible for performing that action or that task, and in collaboration with other agents. Collaboration is how, because we need interaction to perform for multi-agent system, how we are here, how agents collaborate with each other or how they communicate with each other. So some of the papers on multi-agent system, here we have formal specification guided tasking. In this paper, they try to model each agent using a weighted transition system, and the teaming property or behavior is captured by performing composition or by performing multiplication of each weighted transition systems. However, this is not scalable because the system is centralized, plus performing composition in a large scale is too much expensive. And there is another paper, event-based supervisory control. Here, the supervisor by systematically enabling or disabling actions or events, it try to guide the agents or the robots to perform a certain task. Here again, also because the supervisor is a control, it is somehow centralized system. Here we have mixed integer linear programming. Mixed integer linear programming, it has many advantages. It gives you the optimal solution for a task. However, whenever there is a change or whenever there is when agents operate in a dynamic environment, this calculation has to perform it again and again, which can be time consuming. And in 2016, there is a paper, BT-based planning and tasking. In this paper, they try to introduce a very large behavior tree. And once from the behavior tree, they try to assign agents part of the task. However, it was not discussed. They didn't discuss how they generate the behavior tree, and also having a very large or global behavior tree is not efficient. So we'll try to address these issues in this work. So our proposed solution is to develop a hierarchical automatic behavior tree generation method for coordination of multi-agent system. We used behavior tree because they are modular, hierarchical, and reactive. I will discuss this property later. The idea is we have a task. From the task, we want to generate a behavior tree. So the behavior or we can say it is a plan. For the task, we generate a sequence of action or a plan based on behavior tree. So when agents execute the behavior tree, indirectly it is accomplishing the task. So because there are multiple agents, we use market-based auctioning for the interaction among agents. So why we select behavior tree? Mostly in control application, we use finite state automata to represent high-level logic. This is mostly in control. However, they have issues. They have some drawbacks, finite state automata. When we consider their scalability, if we consider finite automatic having n state, the transition will be n square, maximum of n square. So if we have a big transition system, the transition will be huge. Maintainability, when adding or removing state, we have to consider all the incoming and outgoing transitions, which can be sometimes tricky, and as a human, we might forget. Reusability, again, reusability because states, they have some coupling, especially if they have strong coupling. Removing a state is not easy, so we have to it requires another task to perform to remove a state. So to remove a state, so they are somehow challenging. Readability, again, if we have a huge number of states, it will be very difficult, especially with a lot of transition. It will be very challenging. In comparison, behavior trees, they are scalable because they are hierarchical and modular. Maintainability is easy because you just add or remove the part of subtree just simply to the tree. Reusability, it is reusability because of the hierarchical and modular property. We can reuse them very easily. They are readable because in finite state automata, it is bidirectional, but here it is directional. So we can read behavior tree from top to bottom, left to right. So it is easy to read. Structures of behavior tree as a background. Behavior tree are common in gaming industry. However, for robotics, for our domain, they are relatively new. In fact, in 2017, there is a patent that's awarded to a company from Germany is demonstrating a BT for robotics application. So behavior tree, what are behavior tree? Behavior trees are a graphical mathematical model for execution of tasks with inherent hierarchical, modular, and reactive property. Basically, behavior tree has three type of nodes: root node, composite node, and leaf node. Root node is node where execution starts. Composite node, they adjust the flow of control. Here we have two type of nodes. Control or composite node. We have selector nodes and sequence node. Selector nodes are represented by question mark. Here you can see by it's represented by question mark. Here, selector nodes are give us the possibility that if action 1 fails, we go to action 2. If action 2 fails, we go to action 3. But if action 1 perform correctly, we don't worry about the others. And selector node, as the name implies, sequence node, as the name implies, all action has to be performed in sequence. So action 1, action 2, and action 3 in sequence. And we have parallel node. Parallel node give us the possibility to execute more than one action at a time. So instead of one, we can execute 2 actions at a time using parallel node. We have this is for composite node. For leaf node, we have action node and condition node. Action node, it is a computational block, or it can be an actuator for a robot. And we have a condition node. It is the sensor block. Basically, it checks some condition and tells us whether it is it passes some condition or not. In figure A, you can see if condition 1 is okay, we can perform action 1. So behavior tree, I mentioned they are modular, hierarchical, and reactive. As imagine as we have a specification, search for an object, return to base, activate camera, replan. They are modular because we can map each mission, each specification to a sub-BT, as you can see. For example, a return to base, if mission is complete, we can have at the second sub-BT. Each specification can be mapped into BT. They are hierarchical because the flow is from top to bottom and from left to right. Every time the execution is from left to right and top to bottom. They are reactive because we can guard each action by a condition. For example, for the specification the specification number 2, we have the condition fuel low or mission complete. If that is the case, we perform return to base. So they are, by guarding each action with a condition, we can incorporate reactive property in behavior tree. So the contribution of our work is we developed a systematic approach for automatically generating behavior tree coordinator to guide and coordinate autonomous vehicles to satisfy the goal of a mission on need-based. Here, when we say need-based, if an agent can perform the task by itself, it doesn't have to perform collaboration with other agents. However, if it needs to collaborate, because it needs, we must perform collaboration. So the 3 key points we addressed: autonomy, we address it by synthesizing a behavior tree or by synthesizing a sequence of action to meet a goal. Collaboration, we have 2 types of collaboration, level 1 and level 2. For level 1, it is for the entire task, and for level 2, it is for single action. A task can have multiple actions. So if an agent can do all the action by itself, it doesn't have to perform level 2 auctioning. But if it can perform only some part of the actions, because it has to delegate the rest of the action to other agents, it has to perform level 2 auctioning. For distributed decision making, each agent is responsible for the task that is assigned, or for the action or for the task that is assigned to that agent. So market-based auctioning process we used is a market-based auctioning. Generally, in market-based auctioning, each agent try to maximize its benefit, even if there is collaboration, but they are trying to maximize their benefit. So that is a property of market-based auctioning, and it has 4 stages: announcement, bidding, submission, and contract. For announcement, the auctioneer announces a task. Here, the announcer will announce a task. And bidding, the capable agents perform a bid. Here you have 5 agents, but since the task requires aerial vehicle, only the drone and the helicopter will perform a bid and submit their cost of the task or the action. Then once the cost is submitted to the auctioneer or to the announcer will select the agent with the minimum cost and perform a contract. Once the contract is finalized, it means the task or the action is assigned to that agent, and that agent is responsible to accomplish the task or the mission, or the action. So formally, we can state the problem. Consider a mission which consists of several tasks. Tj is equal to j is equal to 1 from 1 up to n. Each task will be associated with a cost function, with a cost fj, and we have a set of robots Ri, I is equal to 1 up to m. Each are capable of accomplishing certain action. We have an action bank ak, k is equal to 1 up to l, so we have a total of l action. So, and each agent capability is indicated by a hat ik. If a hat ik is equal to 1, it means the agent I can perform action k. Otherwise, it cannot perform action k. Given this, the problem is how we can synthesize a behavior tree for the robot R to meet the goal CJ, or the mission's goal CJ, while minimizing the cost fj. So here I already explained the autonomy, collaboration, decentralized decision making. But on the flowchart, we have the green one, which is done by the mission controller, and the blue, the light blue boxes that are supposed to be performed by agents. So the mission controller issue a task T1 from 1 up to n, and the agents will perform collaboration or perform auctioning. Then they send the cost of the task. Once the mission receives the cost of the task, it will select here, as shown in the by the arrow, it will select or will assign the agent that provides the minimum cost. Once the task is assigned, the mission controller can go to the next task assignment. But as the agent that the task is assigned to has to synthesize a behavior tree and perform the task has to execute the behavior tree to meet the goal of the task. In more detail, we have here market-based auctioning level 1. Here we are just talking about task. As I mentioned earlier, can be multiple actions. So the agent can accomplish the task either individual or in collaboration. If it requires in collaboration, it will use level 2 auctioning. Otherwise, it will only use level 1 auctioning. And to be part of the bid at the task level, an agent must be capable of completing the final action of the task. This is, this is logic from logic point of view. If a task is assigned and if the task has like 10 actions, the last action is the one that meets the goal of the task. Even if the other actions are important, but the last one is the one that accomplishes the goal. So only agents that can perform the last task, we assume, we allow only those agents to perform bidding at the task level. At this level, the mission controller is auctioneer, and each agent has to minimize this cost. Alpha Fij times beta Tij. Fij is execution cost, and Tij is duration cost. And they are subjected to these constraints, which enforces only one task is assigned to one agent. So when we expand the costs for the operational and for the durational, for the operational, it is AI JK. As you can see, it is an agent can perform the task. AIK will be 1. So the action, it will be the cost of F bar IK will be the cost of that action. Otherwise, we have to delegate the action to other agents. Then if the task has or if a task has 10 actions, the cost from all action has to be summed up. The same applies for the duration cost. Then by modifying alpha and beta, we can give more emphasis either to operational cost or to the durational cost. So that is a level 1 auctioning for task level. This is level 2 auctioning. For level 2 auctioning, it is similar, but here we don't add actions because we are delegating a single action at a time. So the cost will be again the alpha times the cost of the operational cost of the action plus beta times the durational cost of the action. And this constraint enforce that one action is assigned only to one agent. When we go, that was the mathematical description of our proposed algorithm. When we go to our algorithm, I mean the mathematical explanation of our framework. When we go to the algorithm explanation of our framework, here we start with algorithm 1, which is the main BT synthesis and execution module. Here, every time we initialize our behavior tree with a goal, CJ, then we have number 3, we have a parallel. Here we have parallel node because to allow agents to execute multiple tasks at a time. Then we have a loop from 4 to 17. The loop, we can divide it into 2. The execution is a synthesis part. The execution part, it is from 5 to 11. So when if the behavior tree at the current state can be executed, we execute it. Otherwise, we have to identify the reason why it is not executing at number 12. So we have to identify. After identifying the cause, we have to find a subtree that can meet the failed condition at number 13. And the loop will terminate only when the goal is achieved. So for algorithm 2, we received the condition why our behavior tree is not working. So we try to identify an action that can meet the condition CIF. After that, if CIF is not null, we synthesize the subtree using local action. Otherwise, we have to delegate the action to other agents. And this is the auctioning module. For the auctioning module, we receive a condition. From the condition, first, as I explained earlier, we announce it. After announcing, we wait for agents to submission. After submission stage, we select the agents that have minimum cost. After that, we perform a contract. And this is the details of our algorithm. So it starts with the auctioning algorithm. So the algorithm 6, it is a mission controller. It announces task and wait for submission. Meanwhile, all agents will perform bidding based on in response to the task announcement. Based using algorithm 7, they perform bidding. Once the bid is completed, the mission controller will select an agent, and there will be a contract with the selected agent. When the contract is concluded, as you can see from algorithm 9, we go to algorithm 2. Algorithm 2 will initialize the behavior tree with a goal condition, and we perform behavior tree synthesis and execution in algorithm 3. This is how our algorithm works. So to validate our algorithm, we provided 4 lemmas. Lemma: a conflict-free behavior tree always exists because of the algorithm. It is always conflict-free, and we have a deadlock-free BT. and a live lock free BT, a deadlock free BT, because when building the action bank, we can exclude all actions that have cyclic dependencies. So the reason why deadlock occurs is because of cyclic dependency. We avoid all when building the action bank. We have a live lock free BT. By us, live lock free BT, it's because we assume that the environment cannot infinitely invalidate the action. So at some point, the action will succeed. And a finite time, because all actions are finite, the behavior tree will terminate in finite time. So based on this lemma, we provided proof that a theorem that the proposed decentralized behavior tree addresses the problem one or the proposed problem. So we perform the complexity of our proposed algorithm. The complexity of our proposed algorithm can be divided into two by analyzing the synthesis and execution parts separately. Here for the synthesis algorithm, assuming that we have a lookup table for each subtree, the complexity will be order of 1. But for n agents, there might be an agent might delegate an action. So if we have m agents, the complexity of the delegation will be order of m. And to perform also conflict-free check, we perform conflict-free check by comparing each action with all actions. That's why we have m plus n. And for n action, the synthesis algorithm has order of m plus n times n complexity. For execution, it is easy. It will be order of n, which is order of the action. This is a theoretical background. For the implementation, our goal is to synthesize a BT automatically for a task, facilitate the synthesis and execution of BT in a collaboration environment, using multi-agent systems. So because ROS is the mostly used framework for robotics application, we selected ROS. In addition to that, ROS provide a lot of package and tools. It has distributed communication architecture, which is ideal for a multi-agent system, and it is open source. Because of that, we are using ROS for the implementation. Our idea is we have robots here. We can see robot 1 and robot 2. Both of them will have the BT synthesis algorithm, and if they have based on the task, if there is a need for collaboration, they will collaborate using a topic, that is using ROS topic. There are multiple behavior tree packages available now, but they are not complete. But the one that we found more complete is behavior tree.cpp. So this package has both the visualization and the execution engine together. The visualization engine, you can see the behavior tree you synthesized, and you can monitor the behavior tree, so it is easier to debug. And the execution engine, as you can see, it accepts C++. It is based on C++, and it accepts an XML representation of a behavior tree or an actual hard-coded behavior tree. Then it performs execution. But here, you can see we have the hard-coded version on the left and the XML part on the right. For the hard-coded behavior tree, you can see we have action, condition, we can set timer, and we can execute finally once we design the behavior tree. However, it is fast because it is hard-coded and there is nothing we have to load. It is fast. However, it is difficult to debug also to modify. It is not possible to modify at a later stage. Because of that, we go with XML-based behavior tree, which we can load dynamically, and we can the tool also works with only with XML-based behavior tree. And because you can see your behavior tree, you can debug it easily if there is an issue. This is an example of XML-based behavior tree. As you can see, we have action. So action is listen. We have action. Actions are represented by action keyword. We have fallback. Fallback, they use the name fallback. But selector node is the same as fallback. So by using the fallback or sequence, also we have a sequence node here. We can construct the behavior tree according to the desired goal. Also, we have condition keywords to indicate if there is a condition, if a node is a condition or not. So to summarize, this is the available behavior tree package. Our objective is to generate the XML file automatically so that so that we can accomplish the goal automatically. So that agents can synthesize the behavior tree automatically and perform or execute the mission autonomously. Here, the interaction between the behavior tree and the action node, I want to say something here. ROS has many ways to interact, like topics, services, or and action libs. The one we selected is the action lib. It is client server. It has client server communication model. So the client here is the behavior tree. So the behavior tree will trigger the action. The action will perform the assigned task, and it will report back. Also, since the client at this stage is a behavior tree, the behavior tree can request to check the status or the result or feedback. Based on that, we can say if an action, if a behavior, a subtree is still running, or if it completes or if it fails by checking the status of the action server. I will come back to it later. For a single agent case study, we consider the case that the mission objective is to deliver an object O to a specific place marked by M near position P. Our objective is to deliver an object. The drone has to deliver an object to the position M. So the UAV must perform searching, and when it is near the position, it has to detect the target, the red circle, and it has to deliver the object. That is the objective. So the UAV has the following actions. It has moved to, detect, and deliver actions. Each action has precondition and post-condition. For example, for delivery, the UAV has to be at the position, that the required position, and also the red circle or the M has to be detected. If these conditions are satisfied, then the effect will be, or object O will be at position P. So initially, since the task is a goal, since the task is O has to be at position P, that will be sent to the agent. So our behavior tree will be initialized with the goal condition O at P. Then, since O at P is not executable, we have to perform we have to identify the issue and perform synthesis. So the issue here, O at P failed. The reason why it failed is because these two conditions are not satisfied. So here you can see we identified the action that can satisfy the condition O at P. So UAV has to be near P and UAV M has to be detected. Then we can perform action deliver. If we can perform action deliver, it means our condition O at P will be satisfied. However, again, because UAV is not at position P, we have this will not be executable. So we have to again expand UAV at P. So UAV at P, when we expand it, it will be satisfied by the move to action. So that is why we have here. So we have to expand each condition to have a complete behavior tree. Once we have a complete behavior, we can perform the execution of the behavior tree to satisfy the mission goal. Here I will show you the behavior tree synthesis. So we have this will be it will automatically synthesize the behavior tree from the mission goal. So as you can see, here you can see it is the one I discussed earlier, but I added also here the peak functionality. So R has to be the robot has to be near position P, and M has to be detected, then it has to be delivered. But I added if just in case if the object is not on the hands of the robot, we have the peak action here. So each when we expand it, it will be expanded like this. So the detect, when we expand it, we have a condition, and the condition will be satisfied by the detect action. So earlier I mentioned about the server and client. The server is the action, and the client is a behavior tree. The behavior tree just its task is to trigger the right action. If the action is triggered, and it performs the action. And this is a simple case which I'm demonstrating. So we initialize a turtle bot. We initialize the task, and now we are running the behavior tree. So so the behavior tree for this case, it is simple. I only implemented the move to, that's why I'm showing you the move to. The peak and the detect, they are not implemented, but I will implement the future demonstration. But for now, just for the move to, the behavior tree shown here, that will be executed and to satisfy the mission goal. For the multiple case, this is for the single agent. For the multiple agent case, given the mission composed of tasks described by table 4, we have, the task table 5. We have tasks, task 1, task 2, task 3, task 4, and task 5. And we have resources or agents, UAV1, UAV2, UAV3, UAV4, and a bank of actions. We have move to action, reconnaissance, pick, attack, deliver, and repair action. For the move to action and for the reconnaissance action, the cost is a function of distance, but for the others, to simplify, they are constant. The operation and the duration, they are the cost is constant. And UAV1 can perform A1 and A4. A1 is move to, and A2 is reconnaissance. So each agent will perform some of the actions. Based on this, our objective is to synthesize a behavior tree to meet the tasks, task 1, task 2, task 3, task 4, and task 5. So here, considering task 1, it's a sequence of reconnaissance, move to, and attack. So since all agents that can perform at task level bid are agents that can perform the last action, attack can be performed by attack is A4. A4 can be performed by agent 1. So agent 1 is the bidder at the task level. Agent 1 can perform attack and move to, but it cannot perform reconnaissance. Since it cannot perform reconnaissance, it can perform delegation. That's why it's performed here at row 2. You can see A2 is delegated. So A2 can be performed by UAV 5 or UAV 4. UAV 5 or UAV 4. And the cost for performing reconnaissance by UAV 4 and UAV 5 is shown here. For UAV 4, it is 18.6. For UAV 5, it is 44.6 because they are at different distance, and the cost is a function of distance. They have different costs. So now, after computing the cost for UAV 4 is smaller, so that UAV4 will be selected to perform the task, to be part of task 1. That's why we have here. So the agent that is selected will be UAV4. And this will be for the final task, for task 1 assignment. And this is a behavior tree that is generated for the multi-agent system. And these are the behavior tree. The sub-behavior tree is the auctioning, the auctioning part, level 1, level 2, and the bidding, in the contract behavior trees. And this is the task sub 3 for task 1 and sub 3 for task 2. And this is for the multi-agent system. I didn't perform the ROS implementation. I performed the MATLAB implementation. So here you can see for task 1, robot 4 is assigned to perform action 2. Robot 1 is assigned to perform action 1, and robot 1 is again assigned to perform action 4. So in conclusion, we provided a decentralized on-the-fly behavior tree synthesis framework for coordination of heterogeneous multi-agent robots. We address autonomy using behavior tree, collaboration using market-based auctioning, and distributed decision-making by forcing each agent to be responsible for the task or for the action that it is responsible for. So we have 2 levels of auctioning, as I explained earlier. For level 1, it is task level. For level 2, it is for action. And we provided proof for behavior trees that's live lock, deadlock, and finite time that can meet the assigned task or goal of a mission. And I would like to thank my my teammates from Access Lab and Tech Lab. And I would like to say, I also acknowledge the support from FR-led and US Army and the project Tech Lab. And thank you. If you have questions, I hope we have around 10 minutes.
Thank you,
Of
Rabbi.
questions.
Sorry, thank you, Tadewos. That was really great talk.
Ali, you go ahead.
Yep. Actually, it is now.
Your
open
voice is
for-
low.
Okay. Is it better now?
Yes.
Okay. Thank you, Tadewos. This is really great talk, and I think we can now open it for questions. Any question to Tadewos? So while others are warming up, I ask a question. So what is the bottlenecks, Tadewos? I mean, you have explained so many good things about this one, but what do you see the challenges that you're going to be having as far as using this approach for multi-agent systems coordinations?
I mean,
Unless you're claiming that you have a gold key that can address all problems, are you?
No. The current this framework, it is market-based auctioning. It is based on market-based auctioning. So market-based auctioning by itself, it requires an auctioneer and bidder. So it is somehow centralized. It's not completely decentralized. But if we can eliminate the market-based auctioning that we are working on currently with consensus-based algorithm, we can eliminate the we can completely make our system decentralized. So we avoid partial I mean, because because of the nature of market-based auctioning, we remove the centralization issue.
Okay, so in 1 week you're going to address that problem, and hopefully if people are going to be joining your final defense, you're going to demonstrate that as well.
Yes, yeah, I will demonstrate that.
Okay.
Okay, I know always Rabbi asks question. Rabbi? Question from Rabbi. Okay. All right.
How about
okay.
Justin? I think this work also, Justin is working on that one as well. So maybe questions from Justin also.
Okay. If there is no question, I'd like to make also an announcement. Next week, we are not going to have the seminar series. So 2 weeks from today, Solomon is going to be presenting. Okay. So next week, there will be no presentation. Okay. Go ahead. Somebody was trying to ask a question. Okay. If not, again, thank you, Tadewos.
Thank you.
Thank you so much. Thank you so much.
Thank you. Thank you very much. Thank you for attending my presentation.
Uh-huh.
Bye.
Bye bye now.
Thank you. Bye.
Bye bye.